All right, we're back, and I'm sure you're quite excited to find out, well, what do Collins and Loftus have to say that is different from what Quillian had found out with the teachable language comprehender? Well, Collins and Loftus argued that concepts are connected by associations of varying strengths. Okay, that sounds familiar. We already mentioned that. Here's a different concept that I found a diagram for. So here's, the concept of a fire engine, and then all of its sort of attached things that might be related to this concept of fire engine. And some of them are more strongly attached and some of them are more weakly attached. One of the things they did in this drawing is they implied weakness by having it farther away from the concept. That's not necessarily how things are structured in our brain. You could have a weakly associated concept relatively close to a concept, but just the connection isn't very strong, so that it's not very prone to spreading the activation from the clue to the target or from the target back to the clue. The premise in spreading activation is that once you think about one thing, those strongly associated links will start to just automatically activate the neighbors. And so you might have started thinking about a truck, and then that made you start thinking about ambulance, and you're like, why am I thinking about ambulance right now? And it might be because you've got a pretty strong association between ambulance and truck for some reason, or between fire engine and truck, or between fire engine and red, or something like that. So thinking about one thing so you start off thinking about orange, which makes you start to think about red, which then makes you start to think about a fire engine. This kind of spread of activation happens relatively effortlessly, and you may not have even deliberately made these shifts in thought process. It just happened. You just suddenly found yourself thinking about a fire truck, and you're like, how am I thinking about a fire truck? I wasn't thinking about fire trucks. This might explain some of the conversations you might have had in your life where you start off talking about one thing with your friend. This usually happens with friends, I find, or somebody who you're having a really good conversation with, because you'll start off talking about one thing, and that leads you to start the conversation to move to another topic, which then leads the conversation to move to another topic. And then by the end, you're like, how did we get on this? How are we talking about this? Well, it would be an example of the kind of spreading activation, but this happened interpersonally, right? Like as you thought of something, it caused them to think of something different, and that caused you to think of something, and now our conversation has shifted. Imagine that happening inside of your head. You often may have had this happen with your just thoughts inside your head, where you start off thinking about one thing that caused you to think about something else, and now you're down this weird rabbit hole and you're like, how did I get here? This is not what I meant to be doing. I find that oftentimes happens to me if I pick up my phone to Google something. Like I'm going to Google something I just saw on TV or whatever. I pick up my phone, I see a notification, I check the notification, I watch the reel that was being sent by my daughter. Oh, ha ha, that was funny. Now I Google what was in the reel. Then I, I start going down this rabbit hole of stuff that has nothing to do with why I picked up the phone. Finally, I go, well, that was satisfying. I set the phone down. I go back to what I was watching. I go, oh, that's right. I wanted to look up that actor's name, right? It's like this kind of spreading activation. You've had a bunch of different experiences with it. This model argues something very specific about that spreading, which is that the more closely associated to concepts or details about a concept are, the more likely the activation is to spread from one node to another. So the strength of the connection is the important thing there in determining that spread will happen. So now one thing about, I said you don't have to, you can have an unrelated concept being pretty close to something, and that if the connection's not strong, it won't necessarily activate. But the farther away things are in your brain, the less likely the spread is to just continue, on its own. Because every time, um, remember back to action potentials and how information is shared between cells in your brain. Think about these nodes. I think a good model for it is that they're very much like that they are very much like the synapses between neurons. And so every time you have an intervening neuron, you have the possibility of losing the power that would cause another action potential. And so you sort of, it peters out and you stop thinking about more and more unrelated stuff. You finally get to a point where it's not spreading anymore. And I mean that in physical distance. So typically, related ideas are tied together pretty closely in neural networks. But if you've learned a new concept when you're older, let's say you're in college and you're learning new concepts and you're relating them to things you already know, they may not be physically right next to each other. But if they have a good, strong connection, you'll still have the benefit of spreading activation. But the farther away things are, these concepts are from each other in your brain, the less likely they are to have been organized, to be next to each other because they're related. They're probably unrelated things. So you're not going to go from thinking about that actor's name to thinking about what other movies they've been in to thinking about you know Mars, like unless it's maybe Matt Damon. But maybe I'm just suggesting that there's a cap to how random your associations might become. It probably not just everywhere. Sorry, I have something that I normally do in class, and I didn't want to take it out of my PowerPoints for my recording. So sorry you saw that. So there's another associative network theory that I wanted to mention, which is the feature set theory. And you'll notice these all kind of came out kind of close in time, right? 1968, 1974, 1975. So this was obviously a really hot topic. They were relying really heavily on computers to model how our brains probably work and how we organize things because they were kind of new and researchers were having access to them for the first time. So you see just this flurry of trying to explain how our brains organize concepts. So in the feature set theory, this model says that features of a concept are stored at each node within a network. So here's an example. Here's the concept bird. We have an example of robin. We have an example of ostrich, and they did this one with a dash line for this weaker connection because ostrich is lacking some critical components of bird, right? It doesn't fly. Stronger connection to robin because it has, it matches more of the features, right? And so you have features of a bird can fly, has feathers, has wings. Then you have some sort of coordinate level characteristics of a robin. It's red-breasted, it's small, it hops. Some specific things about ostrich: has a long neck and legs, has it's a large bird, it walks and it runs. So you can see these sort of subordinate level, right? Because bird would be under animal. So sort of subordinate level features, coordinate level features. And because the ostrich is violating something that's super critical to bird, which is it doesn't fly, it's more weakly associated than robin. Um, Defining features are those features that are considered central to the meaning of the concept. So, in order to be a strongly related, exemplar, you're going to need to have as many of these defining features as you can. Certainly these purple ones, right? Um, Down here under the characteristic features, these are features that are strongly associated with the exemplar, but it's not necessary to be a member. So you might see a robin that's not hopping, right? You might see a ostrich that's small because it's a baby, and you'd still be able to tell that it's an ostrich, like those kinds of things, right? It's not, these are characteristics that aren't required in order for you to be able to recognize that this is an exemplar. So according to this model, each of these little features would be stored at a different node, and the more of these defining features that are activated when presented with an exemplar, the more likely you are to recognize that this exemplar is a member of the concept or the category, right? The fewer they have, you may be confused, right? Like you might think, I don't know, isn't ostrich a bird? Right? I know that's how I was with penguins for two. I had, for one thing, I honestly did not know they had feathers because when they're wet, it looks like skin. So I honestly didn't know that they had feathers when I was little. So I thought they were black and white skin like an orca, and then they swim, they rather than flying. Um, and I was like, well, wait, what do you mean that's a bird? Later, when I found out it had feathers, at least it wasn't violating that. Um, but it did still, I'm sorry, it still swam rather than flying. So it's still very confusing. And so you probably have a weaker connection between bird and penguin than you do between bird and robin. Um, According to this model, you take a two-stage decision when you're deciding whether an exemplar is a member of a concept. First, you match the defining and characteristic features, and the more matches that are present, the faster you can respond, or if there's a complete absence of matches. If I show you a zebra and say, is this a bird? You can very quickly respond, no, that's not a bird. So if there are a lot of matches or a complete absence of matches, you're going to respond really quickly. If you have some things that match and some things that don't, that's where you're going to have to literally go through and think about it. Like let's match, let's look at literally the defining characteristics, right? Like let's look and see, does it have the things that are required in order to be a member of this concept? So like with penguin, once you realize those are actually feathers, not skin, and you go, okay, there's feathers, it lays eggs. Okay, it swims. I guess it's probably more likely a bird than something else. I don't know what else it could be, so I guess it's a bird. Like you try and figure it out based like that. It takes more cognitive effort when you have some matches and some not matches than it takes when it's completely like enough, like the defining features are there, you go on. Um, as I'm looking out the window, there's a little chipmunk running around outside my window. And since moving over here onto the east side of the state from the west side, and seeing these chipmunks running around, we've had many a conversation about is that a squirrel? And I'm like, no, it has two stripes down its back. It's clearly a chipmunk, right? And we had to Google it and establish the difference between a squirrel and a chipmunk. We were really struggling because they run around on the ground, they climb up the side of a tree, they make similar noises, they have a semi-puffy tail, not quite as puffy as a squirrel, right? It was very perplexing to us. And here we all are. Everybody I'm talking about is a full-fledged adult. We're all like, what is that? So that happens a lot when you have some things that match and some things that don't. You have to really now put some cognitive effort into it, as opposed to, lots of defining feature matches, quick decision. Absence of any defining feature match, completely easy decision. So it's not only more cognitive effort, I also want to point out that it's more time consuming. And so based on this model, we can predict that if you present a stimulus that has all the defining features, you should respond more quickly. If it's completely lacking all the defining features, you should respond more quickly, and we should see slower processing, revealing this two-stage process is going on when some things match and some things don't. And that's what they've basically found. The typicality effect, they show people these different words, right? So elephant, horse, hippopotamus, goat, aardvark, and so on. And what they find is that the more typical the exemplar is, the more quickly the person can say, yes, that's an animal. No, it's not an animal. If it's in between, or if they're not familiar with it, that's when they slow down. And we can quantify the kind of the cognitive effort, the distance that is occurring, how many features had to be compared in order for the person to make the judgment. And so slower response time implies, more steps in the decision making process. All right. So here we still have our little picture. We're still in the feature set theory. So we have features at each node. We have a two-stage decision process, right? And then we have a category distance effect. I kind of alluded to that on that last page, and I realized, I haven't told you guys that part yet. Typical instances will share more features with the superordinate member of the category. So, if you're at the coordinate level, a typical instance of the subordinate example will share more features with that. More rare instances, more unusual instances will share fewer features with the superordinate. So those typical cases allow for quicker identification. We call that the typicality effect. And we also get that category distance effect. If I have to go up and maybe skip over the subordinate, go right up to the superordinate, this is going to take me longer. And so this theory kind of takes into account, what the teachable language comprehender told us about, having to go up to another level, and then also this idea of nodes that kind of is alluded to by the Collins and Loftus model, the spreading activation model that says, details are stored in nodes that get activated through a spread, and involuntarily you might start thinking about things. In the feature set theory, they say, the farther away something is, the longer it'll take you to make those comparisons. And so this model, it's kind of bringing them all together. All right, let's go ahead and take a break here, and we'll come back in this next segment and talk about categories and concepts.